we are going to learn about the topic of atomic structure, that is part 2. So in this video I am going to cover about certain topics like Heisenberg's uncertainty principle, okay, and quantum mechanical model of an atom, okay, and we are going to learn about distribution of electrons in various orbits and orbitals in the increasing order of their energies. Yes, in other words, it is about electronic configuration and the rules to write the electronic configuration of elements. Okay, about these topics, that means the second part of atomic structure we are going to learn in this video. Okay, so without any delay, let us go into the topic. Okay, so today the topic is what? Structure of atom, part 2. Structure of atom, part 2. Okay, so in this, topics to be covered are what? First one, we will be learning about Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Okay, Heisenberg's uncertainty principle. I'll explain you like a brief explanation will be there, okay, regarding the topic, okay, and we will be learning about quantum mechanical models of an atom, okay, now quantum mechanical model, and finally we are going to learn about what? We are going to learn about electronic configuration of elements and rules to write the electronic configuration. So these are the topics which we are going to discuss in this video. Okay, request all the students to kindly make a note of what all the topics that are being explained by your teachers, okay, and how much ever you keep writing and understanding the concept, the best will be your presentation in your competitive exams. Okay, there are lot many tricks and tips teachers will be teaching you to attempt one answer. So you have to write the notes, okay, make a copy of what all your teacher says and keep practicing regularly. Okay, then only you can see your merit in the results in the competitive exams. Okay, so let us go into the topic for today. What is that? First we will be learning about what? Heisenberg's uncertainty principle. In the name itself it is there. Okay, what does Heisenberg told? Okay, he said that it is very difficult to predict the position and momentum of an electron. Exact position and momentum of an electron cannot be determined, because if you are projecting high intensity electromagnetic radiations, okay, then electron will never be in that position. It keeps changing its position. So it is very difficult to exactly predict what is the exact position and what will be the momentum of the electron present inside a atom. Okay, so that is what is the principle, Heisenberg's uncertainty principle. Okay, so just I am writing for you the statement. It is very difficult. It is very difficult to predict the exact position and location. Predict the exact position. Okay, now to predict the exact position and location of an electron. Location of an electron. Position and location, of course, both are same. We write momentum of an electron. Exact position and momentum of an electron. Okay. So he gave a probability equation for this. If delta x represents the change in position of an atom and delta p represents the change in momentum of an atom, delta x into delta p is always greater than or equal to h by 4 pi. This is what the uncertainty equation of Heisenberg. Heisenberg's uncertainty principle. Okay, here delta x stands for what? Change in what? Change in position of an atom. And p delta or delta p stands for what? Change in momentum. P stands for what? Change in momentum. Okay, so it is very difficult to exactly predict the exact location and position of an electron it is very difficult for us to determine. Okay, that means it is in controversy with what? Bohr's atomic model. Okay, so that's why he gave inequality, uncertainty equation. Okay, so based on this you will be getting small numericals also. Okay, you have to remember. So this is what Heisenberg's uncertainty principle tells you about. Next we'll move on to quantum mechanical model. Let us keep the side heading. What is it? Quantum mechanical model. Quantum mechanical model of an atom. Okay, what is this quantum mechanical model of an atom? Okay, now what is quantum mechanical model of an atom? So on the basis of dual nature of electron, we have already learnt about the dual nature of electron. If you can able to visit my channel, you can see the playlist from the topic of atomic structure. You can identify certain videos in that playlist. Okay, you can have a complete idea about the topic, right? Okay, please visit my channel and do not forget to, yes, subscribe to my channel, right? Quantum mechanical model. So on the basis of dual nature of electron and what we call Bohr's atomic model, okay, and based on Heisenberg's uncertainty principle, as he was telling, it is very difficult to find the exact location of an electron. Okay, there is another scientist who was telling about the probability of finding an electron. Okay, so quantum mechanical model, in this topic we are going to learn about how much probability is there for finding an electron inside an atom, and where exactly more probability is there to find an electron. Okay, so based on dual nature of electron as well as based on Bohr's atomic model and keeping Heisenberg's uncertainty principle in mind, okay, this quantum mechanical model has been introduced. Okay, so this was first given by whom? Yes, Schrödinger. Schrödinger gave one wave equation. So what is this Schrödinger wave equation? We have to know about this Schrödinger wave equation. If you can able to learn about this Schrödinger wave equation, okay, we can understand what is meant by quantum mechanical model. Okay, so Schrödinger gave one wave equation which tells you mostly about what the probability of finding an electron, where exactly the more chances will be available to find an electron. Okay, so what does this Schrödinger wave equation will tell you? It is given by one equation, dou square psi by dou x square. Dou square, here dou square psi, this is psi. We'll discuss what are the terms in that. Dou x square plus dou square psi, this is psi. You have to read it as what? Psi by dou y square plus dou square z by dou z square plus 8 pi square m by h square into E minus V. 8 pi square m by h square into E minus V, okay, is equal to 0. Okay, now is equal to 0. This equation is called as what? Schrödinger wave equation. Okay, so in this here psi represents what? It's a differential equation actually. That's why I told you first only this Schrödinger wave equation helps you to find out the probability. Probability means what? A chance of finding an electron. Okay, chances, 50-50 chances if they are there, or maximum 90% chance is there to find an electron, where you will find 90% chance to find an electron, or where you will get only 50% chance is there to find an electron, or where there is no chance of finding an electron. Everything can be predicted with the help of Schrödinger wave equation, and that only you are calling it as what? Quantum mechanical model. Means what? Actually where, okay, there is a more chance to find an electron inside an atom. To predict that, this wave equation helps us. Okay, here psi represents what? Psi, this symbol represents what? Wave function. Okay, that means it is useful to find out probability function. Okay, probability function. Okay, and in all the three dimensions of x, y and z axis, okay, because that orbital I think you have an idea about orbital. Orbital is the region or space where there is maximum probability of finding an electron. Okay, so the orbital will be in three-dimensional structures. So that's why along all the three axes like x, y as well as z axis, okay, the probability is being predicted. Okay, please understand the point carefully here. Psi stands for what? Wave function. Okay, and x, y, z along all the three directions probability we are predicting for the probability. Okay, and here m stands for what? Yes, mass of the electron, and h is what? Planck's constant. Okay, and E and V, what are the E and V? E is the total energy, whereas V is the energy of the electron. Please understand carefully. Okay, okay, he is total energy, that means Ke and P. E is total energy and V stands for energy of the electron only. Energy of the electron. Okay, pi stands for it's a number, you know. M is for mass of the electron and H is for Planck's constant. So what does the Schrodinger wave equation is going to predict for us? Means it is going to predict where exactly the probability is there to find an electron inside the atom. Okay, so let us learn about the different features of this Schrodinger wave equation and what is the speciality of this Schrodinger wave equation. Let us understand about it. Okay, so an atomic orbital is a product of two factors here. He is telling about what? Probability. Okay, so that means he is telling about what? Atomic orbital. An atomic orbital is a product of two factors. Remember, an atomic orbital is a product of what? Two factors. What are the two factors? Product of two factors. So what are the two factors which you have to keep in your mind to predict the possibility of finding an electron? First part is called as radial part. Okay, radial part. First part is called as what? Radial part, which is called as R. And second part is called as angular part, which is denoted by, here radial part can be denoted even by capital R, and angular part is denoted by theta. Okay, that means if you have to find out the exact probability of finding an electron, you have to consider two factors for an atomic orbital. An atomic orbital is a product of two factors. One is called as radial part and another is called as angular part. Okay, so if you are going to learn about these two, then you will be understanding about this wave function psi. What is the use of this equation? You will be understanding. Okay, there is nothing much to remember, of course, and most of the questions will be asked mostly about the values, the parameters which are there in this Schrodinger equation. That's it. Okay, not much about that. Okay, so here radial part depends on the distance and tells us about the size of the atom. Okay, radial part depends on the distance. And tells you about what? And tells you about size of the atom. Okay, size, total size of the atom. Okay, now total size of the atom. Whereas angular part, what does this angular part tells you about? Depends on the angle variable theta and phi. It gives about shape of orbital. Okay, angular part depends on theta. Depends on angle theta, and it gives you information about what? Shape of the orbital. Okay, shape of the orbital. Okay, totally what does the Schrodinger wave equation tells you about? That you have to remember. It tells you about the probability of finding an electron. That means it is going to tell you about atomic orbitals only. Okay, atomic orbital means what? It is the region or space where there is maximum probability of finding an electron. Okay, so it tells you about what? Prediction of atomic orbitals, or where there is more chance to find an electron or where there is zero chance to find an electron. Okay, so based on these two we are going to understand that, and this can be understood with the help of what? Radial probability curves. Okay, that means radial probability curves are being drawn to predict where exactly an orbital can be found. Okay, now, or an electron can be found inside an orbital, where exactly an electron can be found. You can predict that. Okay, so radial probability curves. Radial probability curves. What does these curves tells us about? Okay, so what does these radial probability curves tells us about? Okay, if you can able to understand that, then you can able to understand what we call the quantum mechanical model of electron and important features regarding that. Okay, so radial probability curves or radial distribution curves, what are those? Yes, radial probability curves or radial distribution curves. What are the features? Features of these curves. Okay, means graphs were drawn to predict the position of an orbital. Okay, you just can predict, but you cannot say that it is only the exact position, because atom itself is smallest, and inside the atom we are having lot much empty space is also there, and nucleus is also there. Okay, so what does that radial probability curves will give information about? You have to learn about that. So features. So they give information that the first point which everybody knows is the probability of finding an electron inside the nucleus is totally zero. This is the first point which you have to remember. The probability of finding an electron. The probability of finding an electron. Okay, now finding an electron inside the nucleus is totally zero. Okay, now it is zero. That means inside the nucleus you cannot find any single electron also, because nucleus is fixed with what? Yes, neutrons and protons. Okay, so inside the nucleus you will not find any electron. So probability of finding an electron inside the nucleus is equal to what? Zero. That is the first feature of what we call radial probability curves. Okay, and next, as the distance from the nucleus increases, the probability of finding an electron also increases. Second point is what? As the distance from the nucleus increases, as the distance from the nucleus increases, okay, the probability of finding an electron also increases. Okay, now the probability of finding an electron also increases. And as you know, all of you have already aware of writing electronic configuration. Okay, so first orbit to second orbit, number of electrons present are more. In first orbit only 2 electrons are present, in second 8 are present, in third 18 are present. So more number of electrons keeps increasing as you go away from the nucleus, isn't it? So as the distance from the nucleus increases, the probability of finding an electron also increases. Okay, this is the second feature of what? Radial probability curves. Okay, so you are learning them in a short. Okay, that's why I am giving all these points to you on the board, right? And next, third point is what? Okay, now third point is here when you are drawing the curves, you will be getting peaks. Okay, so suppose if a curve is like this, drawn between what? Probability function d or psi is taken on y-axis and radial distance r is taken on x-axis. Okay, radial distance r is taken on x-axis. Okay, these peak points indicates what? Suppose this is nucleus. Okay, that means where exactly the peak is coming. Okay, that distance is called as radial distance for that orbital. Please understand the point carefully. This distance is the radial distance for that particular orbital. Okay, that means at a distance of, that means suppose if you go for 1s orbital, Okay, the peak appeared at a distance of 0.53 angstroms. Okay, that means first peak where it is observed, there exactly the first orbit is going to get located. That means it is at a distance of 0.53 angstroms from the nucleus. Your first orbit has been located and there is a chance for finding electron in that first orbit. Okay, so peak points indicates what? You can predict for the possibility of existence of an orbit over there. If orbit is going to exist, orbital also will be existing in that. Okay, so that is what radial probability curves tells you. Okay, so here to find the number of peaks, you have one formula. Okay, what are the different formulas? Okay, to find the number of peaks, to find the number of peaks, you have one formula. What is that? I think you all know. Yes, n minus L represents the number of peaks, where n stands for what? Orbit number, and L stands for azimuthal quantum number. Okay, n stands for principal quantum number and L stands for what? Azimuthal quantum number. We'll be discussing about that also very shortly, very quickly. Okay, at a glance, right? N minus L. Okay, suppose if you are finding the number of peaks for 1s orbital. For 1s orbital, okay, here 1 stands for n value. N is equal to 1. L value for s orbital is how much? L value for s orbital is 0. Okay, L value for s orbital is 0. So n number of peaks, n minus L. Number of peaks represents what? N minus L. So 1 minus 0. Here you will be getting only 1 peak for 1s orbital. Okay, now only 1 peak you will be getting for 1s orbital. If you go for suppose if you go for second example, number of peaks for suppose 2p orbitals. For 2p orbitals, how many peaks are there? Again you use the same formula, n minus L. N value is 2 and L value for p orbital is how much? L value for p orbital, it is equal to 1. So n minus L gives you number of peaks. So 2 minus 1. 1 peak you will find for what? For 2p orbital. Okay, for 1s orbital also you are finding 1 peak only. For 2p orbital also you are finding 1 peak only. Okay, peaks represents what? Okay, the distance from the nucleus where there is a chance of finding an orbit. Okay, that is represented in the form of peaks in the radial probability curves. Okay, and here you will be coming across some other important points are also there, which are called as radial nodes and angular nodes. Okay, you have to learn also about what? Radial nodes and angular nodes. Okay, so what is a radial node and what is a angular node? Okay, these 2 points also you have to remember. Radial node. Okay, and you have another thing also is there, which is called as what? Angular node. Radial node and angular node. Angular node, even you can also call it as what? Nodal plane. Okay, then what is radial node? Radial node is the surface. Okay, now along the length of the radius, it is a surface where there is a 0 probability of finding an electron. It is the surface in a plane. Okay, it is a surface in a plane where there is 0 probability of finding an electron. Okay, it is defined as what? It is the surface where in a plane where there is 0 probability of finding an electron. Okay, now where there is 0 probability, that means you cannot find any electron over there. There is no chance of finding an electron along the length of the radius. The region where there is no chance of finding an electron along the length of the radius of that particular atom. Okay, so where there is 0 probability of along the length of the radius, that's why radial node. Please understand the point. Probability of finding an electron, 0 probability of finding an electron. You call it as what? Radial node. And what is angular node? Okay, now angular node or nodal plane. Okay, it is a plane which passes through nucleus and in which the probability of finding an electron is 0. A plane which passes through nucleus. Okay, now a plane which passes through nucleus where the probability of finding an electron is 0. Passes through nucleus where the probability of finding an electron is 0. Okay, now the probability of finding an electron is 0. The probability of finding an electron is 0. Okay, so these 2 points also you have to remember. Request all of you to make a note of all these points. So radial nodes are given by the formula n minus l minus 1. Okay, now number of radial nodes is given by the formula n minus l minus 1. Please remember this. This is very important for your EAMCET point of view. Okay, how many radial nodes are there for 3p orbital or for 4f orbital? Like that you will be getting questions. Okay, so n minus l minus 1. N represent principal quantum number and L represents azimuthal quantum number. Okay, so n minus l minus 1 if you do, you will be getting number of radial nodes. That means it's a surface in a plane where there is 0 probability of finding an electron, not along the the one which is passing through nucleus. It is in a plane which is passing away from the nucleus. Okay, please understand the point. Okay, and there is no chance of finding an electron. Such surface, you call it as what? Radial node. Okay, so it is given by the formula n minus l minus 1. And angular node or nodal plane, it is given by the formula n itself, l itself. Angular node is equal to l only. Angular node is equal to l value only. L value means azimuthal quantum number value. We know that L values are what? For SPDF orbitals, they are 0, 1, 2, 3 respectively. Okay, now. So, L values are 0, 1, 2, 3 respectively. Okay, please note down all these points. Okay, so you will be getting questions like this. Okay, number of peaks, n minus l. Number of radial nodes. Suppose find the number of radial nodes. Number of radial nodes and angular nodes. Radial nodes and angular nodes for A, 3p orbital. It is a question for 3p orbital, and B for 4s orbital. Like this, a question if it is given. So A for 3p orbital. For 3p orbital, radial nodes are how many? For 3p orbital, what is the formula for radial nodes? N minus L minus 1. Okay, now for 3p orbital, radial nodes is given by the formula N minus L minus 1. So N value for 3p 3 only. For p orbital, L value is 1, and here minus 1 is also there. So that is equal to 3 minus 2, which is equal to 1. So you will find one radial node for 3p orbital. Similarly, angular nodes is L value itself. Okay, now angular node. For angular nodes, what is the formula? L value itself. For p orbital, what is the L value? 1 only. Okay, now for p orbital, L value is 1 only. Okay, for nodal planes or angular nodes, both are same. For radial nodes, N minus L minus 1. Okay, so this is the way in which we will be getting certain small questions for EAMCET point of view. Okay, now for 4s, you can even calculate for 4s. For 4s orbital, number of radial nodes are how many? Radial nodes are n minus L minus 1. Okay, that is equal to what? 4 minus 0 minus 1, which is 3 radial nodes. Okay, now angular nodes, L value itself. angular node or nodal plane, means L value itself. So for s orbital, L value is 0. L value is 0. So angular node is 0 for 4s orbital. Okay, so you'll be getting questions like this based on radial probability curves, and this whole topic comes under what? Quantum mechanical model. Okay, so this is all about quantum mechanical model. Okay, so let us once recall what are the different quantum numbers which we have. We have 4 types of quantum numbers. You all are aware of that. I am going a little bit faster. Quantum numbers. What are the different quantum numbers? We have 4 types of quantum numbers: N, L, ML and MS. Okay, N stands for principal quantum number, L for azimuthal, ML is for magnetic, and MS is for spin quantum number. Right? So N tells you about size and energy of the orbit. It gives information only about the orbits. Okay, Niels Bohr introduced principal quantum number. You all know size and energy. It gives information about size and energy of the orbit. Niels Bohr introduced the principal quantum number. Okay, and it tells only about orbits, and number of electrons that can be placed in each and every orbit is given by the formula 2n square. Okay, where n is the orbit number. So accordingly, in the first orbit you can place only 2 electrons, second orbit contains 8, third contains 18, fourth contains 32, like that. According to the formula 2n square, you can calculate the number of electrons present in each orbit. Already these all topics I already uploaded. Please check and visit my channel, and you can use the what we call playlists which are already available in my channel. Okay, and before you go to my channel, don't forget to subscribe to my channel. I keep on telling, please keep subscribing, keep sharing my videos to most of your friends for the best concepts of IIT JEE and even for NEET students also. Okay, right. Now L stands for what? Azimuthal quantum number, gives information about shapes of orbitals. Okay, now shapes of orbitals, you all are aware of that. S orbital is spherical, P is dumbbell, D is double dumbbell, and F is complex. Right. So next it is L is given by Arnold Sommerfeld. Okay, and ML stands for what? ML stands for magnetic quantum number. It gives information about spatial orientation of atomic orbitals. Spatial orientation of orbitals. Okay, you have S orbital is one type, P orbital 3 types are there, Px, Py, Pz. Okay, 3 orientations are possible for P orbital, 5 orientations are possible for D orbital. What are those? dxy, dyz, dzx, dx square, y square, dz square. Okay, so it gives information about what? Spatial orientations. Okay, in presence of magnetic field, how the splitting of spectral lines are going to happen. Okay, that means he was telling you about what? Zeeman and Stark effects. Right, so ML, spatial orientation of atomic orbitals. Okay, it is denoted by the letter M, and M is equals to 2L plus 1. Number of orbitals for each orbit are given by the formula what? M is equals to 2L plus 1. Please remember, M is equal to what? 2L plus 1. Here L is equals to N minus 1. Okay, now number of orientations that are possible is given by the formula what? 2L plus 1. Please remember, number of orientations is given by the formula 2L plus 1. Okay, like for example, in magnetic quantum number, you just look at this. Magnetic quantum number, in that number of orientations of orbitals is given by the formula M is equals to 2L plus 1. This is very important formula which you have to remember. Okay, so for S orbital, how many orientations are possible? For S orbital, number of orientations means how many directions an S orbital is going to change when it is kept in magnetic field. That is what we are calculating using this formula. M is equals to 2L plus 1. What we are calculating? Yes, we are calculating how many orientations are possible for s orbital when it is kept in a strong magnetic field. Okay, so m is equals to 2l plus 1. L value for s orbital, L value is 0 for s orbital. So number of orientations are 2 into 0 plus 1, means one orientation is possible, and that orientation values are given by the formula minus L to plus L. Orientation values are from where to where? Minus L to plus L. Please remember, most of the children gets confused. You are keeping an s orbital in the magnetic field, then s orbital is changing its direction. See, s orbital being spherical in shape, how many ever directions, even if it changes also, it looks like a spherical ball only. Okay, so it has only one orientation, and that orientation value is 0. Okay, why orientation value is? For s orbital, m value is 0. M value is 0. Number of orientations are 1. That orientation value is 0. Why it is 0? Because it is spherical in shape. A ball, if you turn like this, or upside down, or left to right, right to left, whatever you change the direction, okay, it looks like a ball only. Okay, isn't it or not? You don't have any specific direction change can be noticed there. You don't notice any specific change in the direction. Okay, so m value is 0. Okay, same like that if you go for p orbital, number of orientations for p orbital are how many? M is equals to 2l plus 1 for p orbital. Okay, now for p orbital, number of m values means number of orientations. Please remember, number of orientations are 2l plus 1, and L value for p orbital is 1. L value for p orbital is how much? 1. So number of orientations possible are how many? 2 into 1 plus 1 means 2 plus 1. 3 orientations are possible. That's why p orbital is existing in 3 directions: px, py and pz. 3 orientations are possible, and that orientation values are what? Minus L to plus L. That means minus 1, 0, plus 1. 3 orientations are possible, and that orientation values are minus 1, 0, plus 1. Okay, px, py, pz. You have 3 orientations are there for p orbital. It means what? When p orbital is kept under a strong magnetic field, okay, it will have 3 different orientations, and that 3 orientation values are what? Minus L to plus L. Okay, that means what? Minus 1, 0 and plus 1. 3 boxes. You are going to represent p orbital in 3 boxes, isn't it? 3 boxes together you will draw to represent a p orbital. Similarly, d orbital will have 5 orientations. You have 5 types of d orbitals, and to represent d orbital you will draw 5 boxes, isn't it? So like that, M stands for what? Spatial orientation of atomic orbitals. Okay, and S stands for spin quantum number. And spin quantum number in any atomic orbital, if 2 electrons are present, then they will be present with anti-parallel spins. Okay, to overcome the repulsions, please understand the point carefully. To overcome the repulsions, any 2 electrons which are present in an orbital will have anti-parallel spins. That's why in any the spin quantum number introduced by whom? Uhlenbeck and Gaudsmith. Okay, so in any orbital, if 2 electrons are represented, you are going to represent one with upward arrow and another with downward arrow, which indicates what? Both the electrons which are residing in an orbital will have what? Anti-parallel spins. Okay, and the first one you will be representing it with plus half, and the second one you will be representing it with minus half. Okay, now, so that is being explained in spin quantum number. Okay, so this is all about quantum numbers. Now let us finally move on to electronic configuration of elements. You all have already learned about this topic from your class 9 onwards. Okay, I think most of us will be very happily attempting the concept of, electronic configuration of elements, right? So electronic configuration means arrangement of electrons in various shells and subshells in the increasing order of their energies is called as electronic configuration. Okay, so for this you have to follow this order. One is molar diagram has to be followed to fill up the atomic orbitals. Okay, now molar diagram, just recall. Okay, so based on this molar diagram, okay, based on this energy order, the electrons has to be entered into different shells and subshells based on this order. Okay, in the increasing order of energies, one is less than 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. You have to follow this order, and this you call it as what? Molar diagram. Okay, now this is called as what? Molar diagram, right? So this order you are following. Okay, you have certain rules to write the electronic configuration of certain elements. We have 3 rules mainly. What are those? 3 rules are there. Rules to write electronic configuration of elements, EC of elements. So what are the rules? First one is what? Aufbau principle. Aufbau principle. And second one is Hund's rule. And third one is what? Third one is Pauli's exclusion principle. Pauli's exclusion principle. Okay, you have these 3 different rules to write the electronic configuration of elements. Okay, so what are the 3 rules states? Okay, let us learn about these 3 rules. Okay, yes, what does this Aufbau principle tells us about? Aufbau principle tells us that electron always enters into orbital of lowest energy first. You have 2 different parts to predict the Aufbau principle. I am filling ink in my marker to make it to write a little darker. Always this is only the problem with teachers. Either the cap falls down or the ink is going to get finished, isn't it? Such kind of disturbances, okay, interrupts the class like this. Okay, whatever it may be, let us move on to the topic. What is that? Aufbau principle. So this is only Aufbau principle follows. One is less than 2s, less than 2p, less than 3s. What does it mean? Aufbau principle statement is what? Aufbau, the word building up. The word Aufbau stands for what? Building up. Means increasing order. See, when you are climbing steps or when you want to reach a 5th floor of a building, okay, without going to 1st floor, you cannot reach to 5th floor. Is it possible? Even if you go in a lift, then also it is not possible, isn't it or not? So without going to 1st floor, you cannot directly jump to 5th floor. Okay, same like that, without entering into the lower energy orbitals, electron directly cannot go to higher energy orbitals. That is what Aufbau principle is telling. Okay, so what does the statement tells you about? Electrons always enter into orbitals of lowest energy. Enters into orbitals of lowest energy. Okay, this is the first part. Then how you can calculate the energy? This is the area where you have to focus to get objectives for EAMCET. Yes, energy can be calculated by one formula, N plus L. Okay, whichever is having lowest energy, whichever orbital is having lowest energy, electrons are going to enter into that orbital first. Okay, so if you want to calculate the energy of atomic orbitals, then you will use the formula n plus L. Okay, n plus L. Suppose if you go for 1s, okay, energy of 1s orbital, energy of 1s orbital if you want to calculate, okay, you will go for the formula n plus L. Here n is 1 only, and L value for SPDF orbitals, L value for S orbital is 0, 1 plus 0 is 1. Okay, energy of 2s if you go for 2s, n plus L you have to calculate. That means 2 plus 0, it is equal to 2. Okay, energy of 2s. So, energy of 1s is less than 2s. That's why electron will enter into 1s first. After filling electrons into 1s, then only they will go to 2s. After filling 2s, then only they will go to 2p. Energy of 2p how much? Energy of 2p is n plus L you have to do. Here n value is 2. L value for p orbital is how much? 1. So energy of 2p is 3 units. Okay. So after 2s, electrons goes into 2p. That means electrons always enter into orbitals of lowest energy first. This is the first part of your Aufbau principle. Now if you just keep calculating the energies of the atomic orbitals like this, you just go for energy of 3s. Just look at this area. Look at this area. Energy of 3s. You will use the formula n plus L. So 3 plus L value for S orbital is 0. So 3 plus 0 is equal to 3. See, in both these cases you got same energies. Okay, same energy orbitals. Okay, same energy orbitals are called as degenerate orbitals. What you call? Degenerate. Same energy orbitals are called as what? Degenerate orbitals. Then where the electron has to go? Both these orbitals have same energies. According to Aufbau principle, what is the one which you have to follow? Electrons always enters into orbitals of lowest energy first. But here we have two orbitals with same energies. Then that's why second part of Aufbau principle you have to follow. Okay. If two orbitals are having same energies, then electron enters into orbital of lowest n value. Okay, if two orbitals are having same energies, second part of Aufbau principle. Second part of Aufbau principle. What does this tells you about? If two orbitals are having same energies, okay na, if two orbitals are having same energies, then electrons enter into orbital of lowest n value. Please remember, then electron enters into orbital of lowest n value. Wherever n value is low, there electron goes first. Lowest n value, orbit value, whichever lowest is there, electron goes into that value. Electron goes into that orbit first. Okay, like you have 2p and 3s, as I told you the example here. 2p and 3s are having same energies. Such kind of orbitals are called as what? Degenerate orbitals. Note down this point also, very important in EAMCET point of view. Okay, right. So 2p, 3s. Here low n value is 2 here, but here n value is 3. So electron goes into n is equal to 2. Then only it goes to 3s. Okay, they have same energies, right? This is what you call it as second part of Aufbau principle. Okay, then we'll move on to the next rule, which is called as what? Hund's rule. So Hund's rule of maximum multiplicity, we call it as Hund's rule. So what is Hund's rule? Hund's rule states that electron pairing occurs only after all the available degenerate orbitals are filled with one electron each. This is the statement for Hund's rule. Please remember, electron pairing occurs. Electron pairing occurs electron pairing occurs only if all the available degenerate orbitals, means what? Same energy orbitals. Please recall, what are degenerate orbitals? Orbitals of same energy are called as what? Degenerate orbitals. Okay, so all the available degenerate orbitals are filled with one electron each. All the available degenerate orbitals are filled with one electron each. Okay, that means what? Electron pairing. You are speaking about what? Pairing, electron pairing. See, suppose if you are filling up electrons in p orbital, like if you take the example of oxygen is having atomic number 8, 1s2, 2s2, 2p4. So when you are representing this in box method, okay, 1s2, 2 electrons with 2 half arrows in opposite directions, you are representing. S orbital with 1 box only, 2s2, but 2p orbitals, these are degenerate. 2p orbitals you have to represent with 3 boxes. Now in 2p you have how many electrons? 4 electrons are there. So I want to fill the 4 electrons like this. Okay, this violates the Hund's rule. Okay, what did you do here? Without filling all the boxes with 1 electron, you entered all the 2 electrons in the first 2 boxes only. You left the third box totally empty. This is wrong. Okay, now you left the third box totally empty. Okay, this is wrong way of filling. Electron pairing occurs only after all the available degenerate orbitals are filled with 1 electron each. That means each box has to be filled with 1 electron. Then only pairing should occur. It is like sitting in a window seat in a bus, isn't it? If you are boarding a bus, you will check for a window seat first. Okay, if you are not finding the window seat, then you will go and sit along with the other person, isn't it or not? So pairing will occur only after all are filled with 1 electron. Okay, so that is what Hund's rule tells you. So this is wrong way of filling. What is the correct way of filling for oxygen? For oxygen atomic number is 8, 1s2, 2s2, 2p4. Okay, so this is correct only. 1s is filled with 2 electrons, okay. 2s is also filled with 2 electrons, but while filling 2p, you have to fill all the 3 boxes singly first, then pair them up. This is correct. This is the wrong way of filling. That is what Hund's rule tells you. Okay, so this is very important point. And then next, finally we move on to the third rule, that is Pauli's exclusion principle. What is Pauli's exclusion principle? No 2 electrons in an orbital will have same set of all 4 quantum numbers. See, in an atomic orbital you find 2 electrons. In each box you are finding 2 electrons. If you write the quantum number values for both the electrons, okay, their quantum number values may not be same for all 4 quantum number values, will never be same for both the electrons. That's what Pauli's exclusion principle tells you. No 2 electrons in an orbital. No 2 electrons in an orbital. You just imagine that here orbital is nothing but a box which we are representing in the box method. Okay, no 2 electrons in an orbital will have same set of 4 quantum numbers. Same set of 4 quantum numbers. Okay, like you can take the example of helium is having 1s2. Okay, so in helium you have, in this box you have 2 electrons. Okay, now you are going to write NLMS value for the first electron. This is your first electron and this is your what? Second electron in that orbital. If you write the NLMS values for first electron, means all quantum number values. For this electron, N value is 1 because it is in the first orbit. Okay, L value for S orbital is 0. M value is also 0 because for S orbital orientation is 0. Okay, and spin quantum number value, ms value is plus half. These are the n, l, m, s values for what? First electron. For first electron, n, l, m or ms values are what? 1, 0, 0 and plus half. It is having what? Positive spin. Okay. If you write the same quantum number values for the second electron which is present in the same orbital. Okay. If you write the quantum number values for the second electron. Okay. So if you go for the second electron. For second electron. Okay. Which is residing in the same orbital. Please understand the point carefully. Okay. N value is 1 only. L value is 0, s orbital, 1s orbital, isn't it? So m value is also 0, but ms value, that means spin quantum number value is what? Minus half. So these are the 4 quantum number values. You compare these two now. Here n value is 1, here also n value is 1. L is 0, here also L is 0. M is 0, here also M is 0. But ms value, I mean spin quantum number value, here it is for the first electron it is denoted as a plus half, whereas for the second electron it is denoted as minus half. That means even though their quantum number values are same for the first 3 quantum numbers, they are at least differing in what? Spin quantum number. So no 2 electrons in an orbital can have all 4 quantum number values, can never be same. Okay. They don't have, no 2 electrons in an orbital will have same set of all 4 quantum numbers. Same values will never be same. Okay, na? Same values will never be there for 2 electrons which are residing in the orbital. This is what you call it as what? Pauli's principle. Okay, so this is all about what? Electronic configuration. And you have significance of this electronic configuration, significance of half filled and completely filled orbitals. Okay, now significance of half filled and completely filled orbitals. This is also finally a small topic is there in atomic structure. What is the significance of these half filled and completely filled orbitals? Okay, in other words, you have to go for anomalous configuration of copper and chromium. Okay, anomalous configuration. You have to understand it as what? Anomalous configuration. If you go for copper, copper is having atomic number 29, Cu, copper is 29. Its electronic configuration can be written as what? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, like this we generally write the configuration. But if you observe the last orbit configuration, instead of writing like 4s2, 3d9, you will write like 4s1, 3d10. Okay, this is wrong way of writing the electronic configuration for copper. For copper, the correct way is what? 4s1, 3d10. Here what I did is one electron has been shifted from 4s to 3d. Okay, to have a better exchange energy, you will use the word exchange energy. See, here electron is being shifted from 4s orbital to 3d orbital. So by shifting, what you are observing here, 4s is having only 1 electron, whereas 3d will have 10 electrons. D orbital capacity is also 10 electrons. That means s orbital is half filled and d orbital is what? Completely filled. So half filled and completely filled orbitals are highly stable. Okay, they acquire stability. Okay, because of more exchange energy, because of shifting of this electron, exchange of energy will be there. Okay, more exchange energy will be there. So accordingly, what we call that particular atom, by shifting of electron, they acquire half filled and completely filled configuration, and accordingly it has acquired stability also. Okay, so even for chromium also, generally we will be asked, students will be asked to learn up to 30 elements atomic numbers. So mostly we will be dealing with copper and chromium only. So even for chromium also, 1s2, 2s2, 2p6, 3s2, 3p6, 4s to 3d4. Instead of writing like this, we shift one electron from 4s to 3d. Okay, so that 4s will have one electron, which is considered to be half filled in that s orbital, whereas 3d also will have 5 electrons, which is also considered to be what? Which is also considered to be half filled. Okay, so by doing like this, because of this exchange or because of this shifting of electrons from 4s to 3d, okay, there will be more exchange energy will be there, and that gives stability for that element. Okay, so this is the significance of what? Half filled and completely filled orbitals, and you call this as what? Anomalous electronic configuration. Okay, so up to here your chapter atomic structure has been completed. Okay, and I'll try to upload the EAMCET questions which are going to occur, okay, from this chapter of atomic structure. I'll try to upload as regularly as possible, only if I find my subscribers are increasing like my students. Okay, all my students already they have subscribed. Okay, and I request the new students, those who are visiting my channel for the first time, and those who are watching my videos, please kindly do subscribe to my channel. Okay, your subscription gives me more strength, and I'll make you more and more best videos for your EAMCET and JEE, IIT and NEET preparations. Okay, teachers are very much passionate to upload more and more concepts only with your cooperation, isn't it? If you are going to encourage us by giving more and more subscriptions, then we will do the best for you. Okay, so we are here for your preparation, dear children. Okay, thanks for watching. Your hard work is your superpower. Keep doing hard work and see success in your life. Okay, thanks for watching. Bye.
If you like this video, you just like and subscribe the channel and share this video.